Thanks for the invitation, and thanks for coming. So yeah, so I've heard you've heard about Calabi invariance via contact geometry a couple of times recently. So I wanted to just sort of give the way that I think about some information about how I think about these kinds of problems. So this is sort of a silly title. I just didn't want to make it super long. The thing that I've been working on recently with Joe is using sort of a perspective due to Michael Hutchings from published in 2016 about how to use embedded contact homology to learn dynamical information about surface maps. And he started this sort of perspective for the disk and was able to recover the Calabi invariant, which is classically homomorphism from the kernel of flux into R, using embedded contact homology. And so I just want to sort of explain how we can see this quantity more generally for different surface maps. So here I'm considering maps that sort of come from the Seifert surfaces of torus knots in S3. So come from the standard vibration of S3 by those knots. So I'll talk about sort of the goal and the structure of the problem, explain sort of the two barriers, the two things that are difficult, and then give some background and then explain why these torus knots are a nice case to sort of push the procedure further, sort of topologically, and but still sort of deal with the two problems that can arise when you're thinking about things that are not the disk. Okay, so the goal. So given a surface symplectomorphism, so this is an oriented surface, has a symplectic form, and it has boundary, and then the symplectic form is exact. I'll call its primitive beta. So I'd like to know some very fundamental things about it. I mean, there's been work on this by a lot of people, for example, Frank's Handel, and then a bunch of other people who I'll cite throughout the talk. So I'd like to know, does psi have periodic orbits? And then the second question, if I have a function, I mean, this is something I can just sort of ask for any random function on any random set, but maybe, so say I have a random function on a random set, I'm going to call that set sigma because it's going to be this surface. So does f take any values less than its average? If it takes values greater than its average, then it better take values less than its average. But maybe even better, if I have this diffeomorphism, does f take values on its periodic orbits that are less than its average? So does the average of f on orbits, so I guess maybe not does, maybe is the right verb there, is the average of f on orbits on some orbit less than the average. And that's kind of a natural question I can ask about any function on any set with any bijection, but specifically ECH is well equipped to answer this question when f is this thing called the action function. Okay, so the tool I'm going to use is called the embedded contact homology. I'll write it out at least once. And we'll meet this very briefly later in the talk of y c lambda c. So y here is a closed-oriented three-manifold with an open book decomposition, I guess, with pages sigma, and I'm going to define those things quickly in a moment. And then this is a contact form on Y that's adapted to the open book and its return map is psi. So if you've seen this before, basically what you're doing is you're using the right, so not every surface symplectomorphism can be the return map of an open book. So you sort of mess with this until it can be, construct the right open book, and then the rate flow will give you exactly this map back as the return map. We'll go over that in a little bit more detail later. So then the analogous question is, I guess I'll say here, I'll say rate return map. You can even see that rate return map upside. The analogous question is then, does this contact form have periodic orbits, or the rate vector field of this contact form? And then what naturally corresponds here is there a bound on the action of these orbits? So this is the symplectic action over their linking with a page of the open book. Is this bounded above by the contact volume? And so if I want to set up a dictionary like this, the function f has to be, if I want it to be the thing that gives me the action under this correspondence, f has to be what's called the action function. So it's a function from the surface to R, and it satisfies this condition df is psi pull back beta minus beta. So already, you know, I don't necessarily think that I can answer these types of questions with my tool of ECH if I have just any diffeomorphism in any primitive of my symplectic form, because this might not be exact as a homology, cohomology class. Couple of things about this action function. It's integral, so the integral of f over sigma is called the Calabi invariant. There's been a lot of work recently about, you know, proving that like homeomorphism groups are not perfect and things by finding kernels of these, the map taking, you know, the map that consists of taking the Calabi invariant. The other thing that I wanted to say, oh yeah, is that the action function kind of measures twisting. So there's a way you can think about this as if you sort of take differences at nearby points and integrate that, that will tell you sort of an average amount of twisting that your map psi is doing over the whole surface. Okay, so I think I can fit this on this board. There's sort of two hurdles that I've already alluded to. So the first one is, can I even do this, right? Is this action function even defined? Can I even construct this three-manifold? So the construction F and also my three-manifold. And then two is getting these bounds on the action and linking. So the correspondence, when you construct this three-manifold, the action corresponds to the action function. The linking corresponds to the length of the orbit. That's why I'm taking an average. And then the volume actually is the Calabi invariant. So what I want is on the contact homology side to get, you know, to be able to do this, right? So obtaining action over linking is less than volume in ECH. There's this nice paper of a few years ago, and by Bechara, Senor, Herniovic, and Salomao about sort of understanding the set of action over linking values on the relation between action and linking. So we kind of know generically this takes some sort of, is sort of centered around, they normalize everything properly. So we sort of generically, like for generic psi, we sort of know how the set of values that this left-hand side can take. But given a specific psi, I don't necessarily, I don't necessarily know if I can do this.
Okay.
Yeah.
What's linking?
Oh yeah. So thanks, because I didn't really explain everything very well. I think that might. No, I'll explain it now. So yeah. So the setup is that if I have, so what I'm doing is I'm constructing an open book decomposition on a three-manifold. So this is a closed-oriented three-manifold. So it's a pair. It's of well, it's Y, and then also the binding, which is I'm going to call capital B. This is an oriented link. And then the pages, or actually, I mean, the actual thing is the projection map, but we think about the pages, which are pi inverse of theta for some map, or sorry, pi inverse of theta for some theta in S1. So pi is a map from Y minus the binding to S1. So what you can think of, I have the perfect prop here. If you think about the cover of my iPad tracing out the pages of like a Rolodex, this is exactly what's going on. So the binding would be where my little pencil is. And then here the three-manifold wouldn't be closed, right? It would just be this like cylinder, but you can construct these on all three-manifolds. And so one more thing, it has a monodromy. Which is the return map. Actually, before I say that, so the relationship between linking and linking with the binding and intersection number with the pages. So if I have some kind of another knot in Y, its linking with the binding is the same as its intersection with the pages. And what I'm trying to do is construct an open book where where there's a contact form in the mix as well, and its RAID flow is going to give me some way of flowing the pages to themselves, and then those RAID orbits are going to link with the binding exactly the same number as the corresponding orbits of the diffeomorphism, the length of those orbits. So I'll explain that and then go through the history of this problem, and then explain sort of why these torus knots are really helpful for dealing with hurdles 1 and 2. Okay, so just to say just sort of what I said, but more precisely, so there's a monodromy, which is the return map of a flow, which goes from one page, so I'll just say from page to itself, where this flow has to be transverse to all the other pages, and it has to point, so this is the binding, it has to point in the meridian direction near the binding. It has to go like that. And then, so there's actually a correspondence up to the diffeomorphism type of, or sorry, I have to say something about contact forms first. So if I change this flow by some isotopy, I'm going to get the same, three-manifold up to diffeomorphism type. So if you care about open book decompositions, you might also care a lot about mapping classes of diffeomorphisms of surfaces. And so the reason why contact people like to think about these things, well, there's this correspondence due to Giroux between contact structures and open books. So the idea is that a contact structure and open book correspond if the contact structure on the pages away from the binding is very close to the tangent bundle of the pages. But I'm specifically interested in contact forms. So I'm going to say a contact form is adapted to an open book if the grade vector field is transverse to the pages and it's also parallel to the binding. So it's different than this flow. So that's kind of the important thing, is that the open book is kind of determined by the mapping class of the monodromy, but the contact form I put on it is going to have a rate flow that will be away from the boundary, transverse to the pages, so it'll be isotopic to this flow, but near the binding, it could be doing something different. It will in fact have to be shifting the pages near the binding. And furthermore, and rate flow returns to the same page in finite. So I think you can come up with examples where these first two conditions are satisfied, but this last one isn't satisfied. So we need to require this. So the idea then of this whole story, which is due to Hutchings, I mean, there's the idea of constructing a contact structure that's supported by the open book is much older, but the exact construction that I'm going to talk about comes from this 2016 paper at Hutchings. Is so we want to construct okay, so in this case, sigma is a disk, and we want to construct, construct the mapping torus. Of psi. And then we want to build a contact form on M so that the rave direction parallel to the 0,1 direction. And the time to flow around the whole 0,1 direction is F. So what you should be thinking of here is lambda is approximately equal to F dt plus beta, where beta is my primitive. This isn't exactly going to work, but I don't want to write down the actual contact form because it would take the whole board. Take the whole board widthwise. And then the final step is you glue in solid tori to 0,1 across the boundary, mod the equivalence relation. And you have to do this in the right way to get a manifold and so that your contact form is still defined. But the thing that happens then, the thing that you have to be careful of when you have more than one boundary component, which we aren't going to have in this situation, but which I had in my thesis this is from 2019, but it was published in 2021, is that the monodromy, so this whole setup is going to give you an open book decomposition on some closed three-manifold. So the monodromy is equal to the return map that you started with, psi, but untwisted on the boundary. Oh, and I also want to start with psi being really nice near the boundary. So maybe it's a rotation near the boundary, just for this step. Untwisted on the boundary by the value of F. So this is really not a problem on the disk because there's only one mapping class, only one possible monodromy. But if you have a more topologically complicated surface, especially if you have more boundary components, you can really get, right, so all I know about F is it's differential, and I could change it by some real number, but okay, so maybe I fix that so that the value of F is equal to, some nice amount on the boundary, but then that's not going to, you know, have the same, whatever the same nice property I wanted to pick, is not going to necessarily happen on all the boundary components. So there'll be some contribution by the flux of psi on the relative homology. And we're not going to talk about that anymore today because we have only one, but anyway, only one boundary. But anyway, the point is, if you want to try and do this, you have to be a lot more careful the more boundary and more topology you have. So these have some topology, which is why they're more complicated than disks. Okay, so this sort of idea was used by Hutchings in 2016, like I said, to take disk maps, turn them into contact forms on S3, compute something in their ECH, and then pull that back to the disk map and tell you something about the action function. So what he proved is that if sigma is D2, psi is a rotation by some number of theta naught near the boundary. And the Calabi invariant, which I did not give a name. So V is less than theta naught. Then there exists gamma, which is a periodic orbit of psi. So some finite set of points that psi takes one to the next. And the average, its action function on gamma is less than the Calabi. So this tells you, by a theorem of Frank's, you know that there has to be another orbit, but we didn't know that there had to be some quantitative bound on this dynamical function. Okay, so then there's been some work since then. So the dates get a little confusing because of archive dates versus publication dates. But anyway, if you probably heard about this a few weeks ago.
Using the right color of chalk.
That he did?
Yeah,
really?
He also used red chalk.
Okay. That's great. Okay. So this is nice. Removing hypotheses. And then let's see. I guess I have to. And I think this was posted earlier, maybe in 2019 or 2020, but I think he removed more hypotheses and posted it last 2021 or maybe 2022. I don't quite remember, but so yeah, so I apologize if I've gotten the dates not quite right. And so in between, but the date will be also 2021. I proved that if the surface is an annulus and psi is a rotation by, so it's y plus on one boundary component and y minus on the other boundary component, and it's actually, it matters which one is which. So this is the plus boundary and this is the minus, and this matters symplectically, like based on what the symplectic form is. So it's if I take a curve like this, it will go somewhere like this, but who knows? Do that, we can do this. Just the right endpoint has to be farther than the left. So rotation near the boundary. And Calabi is less than the max of y plus and minus y minus plus f. So this is some sort of flux term that I'm not going to explain. It has to do with what I was talking about here. Then you have the conclusion. And then more recently, so you're allowed to have any surface, and psi is a generic Hamiltonian. So same conclusion. So that's really nice. And so the sort of next step is trying to think about sort of if maybe I can, within this set of sort of maps, can I, if I have a specific map psi, can I get the same conclusion? And also maybe I can think about things that are not isotopic to the identity. And that's a pretty natural thing to do because there are a lot of open book decompositions whose monodromies aren't isotopic to the identity. And I know that my return map or my my surface map is basically the monodromy, but it can differ along the boundary. I said, I said equal. This is up to isotopy. So in progress with Joe Nelson. So hopefully in a few months, you will see this on your computer screens. So this is a genus P minus 1, Q minus 1 over 2 surface with one boundary component. Psi is the rotation by 2 pi over PQ near the boundary. And it's also freely isotopic, so I have to be able to move the boundary to the TPQ monodromy. So monodromies are always the identity near the boundary. That has to do with this condition on the flow. My return maps are never the identity near the boundary because that has to do with the rate flow. The vector has to point in the same direction as the binding. So, and you need some bound on this. So in the ECH world, you need some bound on the volume. Then blah, 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 same conclusion. Maybe I shouldn't say blah blah blah. Then you will be able to find a periodic orbit, and it will have some bound on the average value of the action function in terms of its Calabi invariant. So okay, so I want to study these, and the rest of the talk I want to explain why I want to study these and why I think it might be successful. I guess maybe, the real reason why I want to study these is that I sort of thought about the annulus a lot as a graduate student, and then I thought, what's the next most interesting surface that I can still get my hands on? Well, that's going to be two annuli plumbed together, and there's sort of there's sort of three obvious monodromies, right? I can take, so if I think about mapping classes of two plumbed annuli, so I've got something like this. So this is genus 1 surface, and the simplest mapping classes are can be expressed in Dane twists about these two curves, compositions of Dane twists. And so the simplest one is like, do them both right-handed, do them both left-handed, or do one right and one left. And I've been thinking about this for a long time, and I can tell you what happens when I do them both right-handed. So next 5 years, I'll be able to tell you about one of the other ones. That's the hope anyway. Okay, so I guess the point is contact topology is sort of very local and nice, and you can express things in terms of stage lists, which are very local, and contact forms, like contact structures are very local, and contact forms are very global, and you really have to know about the form on the whole thing to compute any contact invariance. Okay, so the two hurdles that I mentioned at the beginning. So why are these specific examples good for them? So hurdle one. Defining. So the point I want to make here is that this is, in some sense, the same problem as constructing the open book. So to define F, for this we need psi pullback beta minus beta to be 0 in H upper one. And to construct Y, so there's this nice paper of Colon, Honda, and Laudenbach. It's called On the Flux of Pseudo-Inosov Homeomorphisms, where they construct something that can't be the return map of a rate flow. So they construct a map that you can't do this construction for. And the key condition is same thing. So it's not actually quite this, you don't actually quite need something that's strong. This needs to be on the kernel side push forward minus the identity. H flow one. But certainly, you know, and they mentioned this due to Giroux, there's sort of a less like focused on the action function construction, where if you have just this condition on the left, then you're going to be able to construct the three-manifold. And I mean, it sort of is very natural, right? Because you have your, or that defining F and constructing Y are sort of the same thing, two sides of the same coin, because and it's actually nice that I accidentally put this on the same board. If I have a three-manifold with an open book on it and an adapted contact form, I have to have this rate flow returning to the same page in finite forward and backward time. So there's some function on the page that just tells me how long that takes. And that's the same thing as the action function. And so given a symplectomorphism of a surface, you can just ask if such a function, if this function exists, and those will be the ones that you can construct a three-manifold for. So I won't get incredibly into this in incredible detail. The paper here is Colon. Colon, Honda, Laudenbach, I think it's 2013. Or it might be 2008. I think it's 2008. Sorry. I think the other paper is 2013, yeah. And so they have a very nice, very explicit argument that says, you know, if this isn't 0, then you can actually find a surface that's supposed to have, you know, you can compute its area in one way and it has 0 area, and you can compute its area in another way and it doesn't have 0 area, so you got a problem. And then sort of this is just, you know, clearly something that you need if you want to define this action function that I said was defined as a primitive of this one form. But the point is, it's not so bad of a condition. So if I, now I am going to erase this. So psi pullback beta minus beta equals 0 in H upper 1 is not so bad of a thing to ask for. Certainly, right, if I believe there are lots of open books and I can, you know, construct one given any monodromy, then there have got to be a lot of such pairs, psi and beta, but also I can just sort of know given psi if I'm going to be able to find such a beta. So the idea, and I'll just say there's a lemma, if the psi pullback minus the identity action on H or on the closed one forms I mean, I think this is, anyway, is surjective. Then you can find beta with beta equals omega and psi pullback beta minus beta equals 0 in H over 1. So the point is, so the proof basically is, so starting with any primitive, so let's say d beta prime equals omega, then all I need to do is find a closed one form alpha such that psi pullback beta minus beta, or sorry, I think it's easier to write this, psi pullback minus the identity applied to beta minus minus sign is equal to psi pullback minus the identity applied to alpha. So as long as I can find something, so this is just now some, element, this is just some closed one form. As long as I can find another closed one form, satisfy this equation, and I can, by my assumption, then I'm done. So as long as you know something about your map, you'll be able to do this. And you can show, like, for example, for the very simple case of T2Q, you can do this very explicitly. And for all torus knots, you can actually do this very explicitly. You can figure out like exactly what this, you can write down what this is. Okay. So I think the next thing I want to talk about is how to get, is the sort of the second issue, which is how to get the bounds in ECH. But first, before we move to that, does anyone have any questions about this? Okay. I guess I could, let's see. Okay, so what we want to use is a invariant of knots in ECH. So the idea that's sort of hurdle 2 action over linking is less than the volume and ECH. The thing that's really great about ECH is that it's a diffeomorphism invariant constructed from contact form. So you can pick a very nice contact form, compute something, and you'll learn something about your terrible contact form that you don't know anything about. So that's sort of the goal here is construct some invariant from ECH that sees these quantities about a contact form and then compute it in a much nicer setting. And then you'll be able to recover something of your original form. So first I'm going to define ECH very quickly, define this invariant, which is called the knot filtration. And then I'll tell you why these torus knots are so nice, and I'll explain that picture. Okay, so the ECH chain complex is generated by certain finite sets of brave orbits of non-degenerate contact forms. So certain means that if you have a hyperbolic orbit, it can only appear with multiplicity 1. And its differential counts embedded J holomorphic curves in R cross Y that are asymptotic to your orbit sets. Okay, so that's the quickest. Oh, I guess I should say, so this is due to Tobbs, I think 2007. This is a ECH is a diffeomorphism invariant. So there are all these choices that you've made, but they didn't matter in the end. You're just going to get the same thing as long as you have the same manifold. So on top of all this, I'm going to put a filtration on the chain complex. So the not filtration given B, which is an elliptic brave orbit, and you might be remembering that I'm using a capital B here, and I used one for the binding earlier. So this is probably going to be the binding of an open book. And it has a rotation number, which is irrational. So what is the rotation number? This is probably most people in this audience know, but some people don't. You can, if you take the Rabe flow restricted to the contact structure over your orbit, you flow around. You can pick a trivialization, but that'll only change this by an integer. And we want it to, so you take that flow, you take its differential, and that will be, if it's elliptic, that'll be conjugate sum rotation based on, classification of matrices in SL2R. And we want that to be irrational. And, the contact form is non-degenerate. So if it were rational, it would be degenerate contact form. And also what you really want for the dynamical things is there's a nice way to pick the trivialization for this form, but we won't really worry about that so much. ECH is filtered, and proving that this is a filtration, takes a little bit of work as well on the asymptotics of homomorphic curves in the differential. So this is not immediately obvious. So it's filtered by this function FB. Okay, so alpha is some set of Rabe orbits that doesn't include B, and B is itself M appearing M times. This filtration is defined as M times the rotation number B plus the linking number with alpha. So alpha is a set of Rabe orbits. You just take all the linking numbers, add them up with their multiplicities. So the nice thing about this filtration is that if you take the homology, so if you stop at a certain filtration level and you take the homology, that's invariant of the contact structure. You could have picked whatever contact form you like. This is the same paper that I referenced many times.
So M can be a non-negative integer, right?
Yeah.
Yeah, okay.
Yeah, so M is a non-negative integer. This has no B's in it. Homology of the ECH chain complex with generators only having filtration level less than a certain level depends only on the three-manifold, the contact structure, the elliptic orbit, its rotation number, and L. So this is great because I much prefer to pick my contact form and within the same contact structure. So the idea behind all of these proofs that I've now just erased all of is that, well, not all of them, sorry, the one due to Michael and myself, are that you compute this homology for all values of L, and that will give you a lower bound linking with the binding of right orbits. So relationship between the ECH index and linking with the binding. And then upper bounds on action come from the ECH Violent law, which is due to Vinicius and Christopher Gardner and Michael Hutchings. So you can play those off one another and get an upper bound on action over linking. So this is all very nice, but to compute such a thing, you actually need a contact form and you need a chain complex. And it needs to be a non-degenerate contact form, and non-degenerate contact forms are hard to get your hands on. So what you have to do is figure out sort of enough properties of a non-degenerate contact form to actually compute the ECH. So the idea is so we can figure out what this chain complex is for all pairs P and Q. And if you're interested in the guts of that, I have a lot of tables of generators I can show you. But the nicest situation is PQ equals 2, 3, which is what I've drawn over there. So the idea for constructing the model when model contact form when PQ equals 2, 3 is the following. So, okay, so my setup is I have the T23 torus knot, the right-handed trefoil. If you are familiar with mapping class groups and open books, you know that that's the one where I take two, I had this picture here of this genus 1 surface, you take 2 right-handed Dane twists, that's the monodromy. And the rotation number, if you remember it from the theorem I just erased, is I need the rotation number on the boundary to be 6, which is 2 times 3. So the goal is to find some contact form on S3 with T2, 3 as an elliptic ray orbit. And its rotation number is approximately 6. So knowing that it has to be approximately 6 sort of comes from various things like if you've ever computed the fractional Dane twist of fractional Dane twist coefficient of that 2 right-handed Dane twists on the punctured torus, that has fractional Dane twist coefficient 1/6. So that's why it's 6. So the idea is I want to write down the return map psi on a page of the open book and perturb it somehow. So I had my whole construction, which I have written over here. So the idea is there is an open book decomposition on S3 with T2, 3 as the binding, and it's got some pages. Those pages are genus 1. So 1 boundary component. And so what I'm going to write down is a return map of the Ray vector field of a contact form which is adapted. This open book, and from that return map I can cook up my contact form, and I can also figure out how to perturb it to be non-degenerate. So that's the idea. And then how will I figure out what my ECH chain complex is? I have to go back to a previous paper of myself and Joe Nelson. We studied the ECH of surface bundles, circle bundles on surfaces, and sort of studied these contact forms that you can get by perturbing Ray vector fields that give you circle bundles using Hamiltonian flows. So the point is that then, so to get non-degenerate, I need to perturb a Morse function on the page that is return map equivariant. And in that case, the generators are the critical points, and the differential. Oh, I did not draw that D the way I normally draw these. The differential counts gradient flow. So in the last few minutes, I will explain this picture, which is sort of doing this procedure for T2Q, or sorry, T23. So what I've drawn is a hexagon on a plane. As you might know, you can think of the torus as R2 quotiented by Z2. So there are a lot of fundamental domains here for the torus, like one's right here, for example. So this is like the x-axis, this is the y-axis, this is 1, 1, 1, negative 1, negative 1. Okay, so what I've drawn is a fundamental, so this is one fundamental domain for the torus in R2 mod Z2. So then what I've drawn is a fundamental domain for the action of psi, and then I've drawn sort of the easiest way to think about it in R2, but you can actually draw the whole thing in here, so I'll do that because it's pretty simple. What you do is psi is just the rotation, so it's the rotation in SL2Z, so it's not immediately just like rotation, but it is, you know, the one that sends, it's the sort of clockwise rotating element of order 6 in SL2Z. It's going to send this quadrilateral to this one, this one, this one, here, here, and then back. And it's really a very convenient picture because I can then find all of the orbits. So the binding of the open book is given by cutting this ellipse out. You can write down what the ellipse needs to be so that this map, you know, so it's symmetric with respect to this map, equivariant. And then the orbits are really easy to find, the periodic points of period less than 6 are easy to find. There's going to be one that's yellow. All of the filled in points, so all the points that are the same are equivalent up to Z mod 2. And then all the points of the same color are equivalent when I also quotient by my return map, this 6 periodic thing. So I'll actually have 2 orbits, one that's yellow and one that's green, that are shorter than sort of the average point that's just in here. And the reason why that's important is when I construct my Morse flow, I'm going to have to make sure that these are the critical points. So I just have to do that kind of carefully in a way that is equivariant. So the last thing I'll just draw is that. Let's leave it white. So I have a maximum sort of up here, and just flow lines like this, and you can check that if you sort of slot this around in all the 6 different places, you'll get something that's equivariant. Maybe we'll just check one. So I want to draw, I want to check that this is sort of a well-defined direction for the Morse flow to go. So it's going like that. Okay, so I rotate by 1/6. So it's going to go from here to here. And then I rotate again. It's going to go from here to here. And then I rotate one more time. And wait. There to there, there to there. Did I do this wrong? Let me check with my notes. Aha. Yes, it's the wrong one. So this one will go to Okay, maybe, I think I've heard people say you shouldn't do arithmetic on the board. Maybe this is something you shouldn't do on the board. That's right.
I'm actually a bit lost. Can we back up a little?
Yeah, we can back
So
up.
what, okay,
That'll
so
give me
how
more
did you
time
get
to
this
fix that.
toric? So this is a toric, kind of toric-ish contact form that computes the not filtered ECH for this T23 knot, right? That
I think you can think of it as toric, but it's much easier to think of it this way because then you can use the S1 invariant, almost complex structure stuff from our previous paper.
but isn't, I mean, so isn't the reason why you need to do this perturbation thing because it's toric?
But this
Or is
isn't
it
a toric.
Is it periodic? Is that?
It's, so this is,
Oh, okay, maybe that's one.
so yeah, so what you can think about this a couple of different ways. You can think about this as like a orbifold Booth-Wong construction
Okay, okay,
on like a 2-3 sphere.
okay. Okay, so the knot complement is
This
like a
one's
goofy
gonna be
wing.
2.
When you like
Yeah,
compacted by the knot complement, you get like a kind of a goofy wing type form.
yes.
Okay.
And this is due to Kegel and Lang. I think their paper was from 2021. They
But
have
then
this
the-
whole construction.
Yeah, but then the computation ends up being similar to the toric case, is that,
No,
because this kind of looks like the toric thing.
there's no differential. And this is, so what ends up happening is,
Oh, what's maybe confusing about the picture is that it looks like a toric picture you would draw, but the point is that
oh yeah, it does.
drawn like a PQ, or you've drawn like a sixgon, and you're trying to understand like how that corresponds to the pages of the open book. You know that your like monodromy is corresponding to like one of the 6 periodic maps of that domain minus the origin. And so you're looking at like what happens when you rotate by 1/6. So the picture Morgan's drawing is actually like a picture of the page.
I see.
Yeah, and I think I also realized, I don't think I want to add to this because I'm going to get too messy, but there's sort of a problem. I mean, this is maybe getting too into the guts of it, but there's a problem that happens that has to do with why this is actually a very difficult case, and like 3-4 would be easier, is that when you go around, so this is why I was getting confused. Goes to here, and it goes to here, here. What am I doing?
I think the green points are Z-mod 2.
Yeah, the isotropy is EMA 2, so it should
It
flip.
should be like critical 1.
Yeah,
Index points.
Yeah.
Or index 1 critical.
should be like this.
Are you drawing arrows for the function f?
No, so this is my Morse function. I don't think this is maybe that helpful. I think maybe I should step back.
Okay.
Yeah, so I think I should also finish up, but the idea, so this is not a toric ECH picture because this is a hole, it's a hole, right? This isn't like a picture on a plane that then lifts to R4 or anything. This is like, okay, one way to draw this without a hexagon would be if I just drew the square, which is which then I can glue up to a torus, and then I'm trying to draw another a fundamental domain of some symplectomorphism of that torus, that then it just makes a lot more sense to see it as a hexagon, because what would happen is this piece goes to this piece, which goes to this piece, which then goes to this piece, then this piece, then this piece. So it's just kind of silly if you draw it on one square. And then the idea is that's the return map of your RAID flow on your open book, and you can take the quotient by that and think about it as an orbit bundle on this thing, and use all the machinery from the previous paper. So there's a way to think of this as almost a circle bundle. And if you wanted to do this for different P's and Q's, you would have to draw a hyperbolic picture just because the geometry is not correct. And then if you wanted to, so if you wanted to do P, like P equals 2, Q equals anything else, you'd have to draw some sort of hyperbolic picture. If you want to do this in general, you have to, there's a lot more topology. And there's a nice book of those Boccian dipshits that kind of explains sort of how to think about these monodromies. And then the last thing, the nice thing is that these green points become a hyperbolic orbit which I'm calling H. And you might, if you've seen any ECH computations, you might be scared when you see a hyperbolic orbit of even ECH index, but it turns out this is sort of an interesting, I just think it's kind of interesting. You see a negative hyperbolic orbit. So it's got even ECH index. In this case, there's no differential. These flow lines are all indexed 2 or higher. Yeah, so if there's any more questions, and I really like this picture, so I'm happy to always talk about it. So, and thank you very much.
I'm still trying to get a picture. So is the hexagon the knot? Middle?
The knot is the middle of the hexagon. Yeah.
Oh, okay. We would throw out to get the pages.
Yeah.
Okay, okay.
Yeah, these all glue together. All these things glue together, and you can, I mean, you could draw them all in this square and glue them together by your normal, you know, the way that you normally glue a torus together.
So I have a question.
Mm-hmm.
So have you thought about the pseudo-Nassau, like let's say I have a knot which has like a pseudo-Nassau fiber knot complement.
Yeah.
Then like do you understand, like, okay, so is that one of these cases? Is that one of these cases?
These are all periodic.
These are all, yeah, I mean, well, sorry. I guess I meant for the plumbing thing you were talking, like this, one of these, because you just immediately drew the meridian thing, that guy, so I was wondering.
Yeah, these are all periodic. Where do I have any space? Oh, I have space. These are all periodic with positive fractional dangerous coefficients. So basically, I don't know if anyone has seen this paper that I like by Colon and Honda from 2013, called Braid Vector Fields and Open Book Decompositions.
Yes, it's like my favorite. It's like my favorite paper that I've ever read.
It's, yeah, and I've read certain parts of it so many times, and other parts of it not at all. So, so there's this really short section about proving that the linearized contact homology of periodic open books with positive fractional dangerous coefficients is non-zero. And so this is kind of, you know, taking some of those ideas in the ECH setting. So there's a couple of, yeah, so I don't know, maybe you want to think about what happens when the fractional Dane twist coefficients are negative. You certainly don't want to think about linearized contact homology. It should be 0. These are going to be over twisted. But ECH isn't. But the problem is the model forms are not going to work as well. There's some other things you have to do near the binding. You might want to think about pseudo-Nassau, or just even a Nassau. Again, models aren't going to be as nice. So yeah, I mean, I think sort of the problem is that these questions are very natural from the side of local modifications to the contact structure, and like really hard from the side of like trying to globally understand what is sort of the most symmetric contact form that has that contact structure.
Sure.
So yeah, I don't know. I would love to understand the knot filtration on the, I mean, it doesn't, this picture doesn't differentiate between any of these knots, but the other 2 knots that have monodromy that are Dane twists in these.
Because I think there's sort of this like, I mean, I was talking about this with someone else recently. It's like, like, you know, there's like this volume conjecture about hyperbolic knots, and everything with pseudo-Nassau monodromy is a hyperbolic knot, right? If it has a fibered knot with pseudo-Nassau monodromy, it's hyperbolic. I think that's like a theorem of Thurston. So, you know, I mean, I think it's very like stupid, but also natural question to be like, is there any relationship between the volume conjecture and the ECH volume property? Because the volume conjecture is an asymptotic statement about the volume, and so is the ECH. So, and that must have factored through some sort of ECH knot thing. But which ECH knot, which version of ECH, which not ECH thing is a good, you know,
and also, you know, how many things do we know about not ECH? There's like 2 papers about each of them.
Sure.
It's like 4 papers about this, right?
Yeah,
so,
but I think a good, I mean, you know, obviously understanding any pseudo-Nassau map from this not filtered ECH property would be a good first step. So anyway.
It would be.
Yeah.
Yeah, I think it would be really hard.
Maybe too hard.
Yeah.
I think you have to start by reading the sections of Colon and Honda that you haven't read before.
Yeah.
It's okay. Well, we can talk about that after. Yeah. Anyway, let's thank our speaker.